Okay, so next example we're going to go over is an RL parallel circuit. So we've looked at the RL series, now we'll look at the RL parallel. This one has a little bit different equations. So again, we're going to start off this video here. If this is your first video, there's a whole playlist here where we're going through all different types of circuits. So we're looking at a resistor and a coil in parallel. So there's our resistor, there's our coil, and the L is a shout out to our buddy Lens. But you can see here that we've got we've already done a number of circuits, series RL, series RC, so you can go back in the playlist and go and check those out after finishing this video. I'm going to do all the equations first on this page, and then we're going to look at an example. So I'm going to look at this example with 2 8 volts at 60 hertz, resistance of 50, an XL of 120 ohms, and we're going to have to find everything else for the circuit. But we're going to build it up first with the equations. So we have a parallel RL circuit. So we know that in parallel, the voltage is the same all the way through. So it doesn't matter what type of animals you have in the circuit, whether they are resistors or resistors and coils, the pressure in the circuit is always the same. So we know that in this case, our total voltage is equal to our resistive voltage, and it's also equal to the inductive voltage. You can literally take your fingers and go across from the source, and you can see that you can go across the resistor and the coil, and you don't go through any other components. So the same pressure is all the way through. So if we had 120 volts here, that 120 would be across the resistor and the coil. Okay? But something must be messed up because we have two different animals in the circuit, being a resistor and a coil. So in this case, the currents are messed up, and they're messed up by 90 degrees. So we have our total current is going to be equal to our resistive current, and we're going to square that guy, plus the inductive current. We'll square that guy, and depending on your calculator, you may need to use double brackets, and then we're going to take the square root of the addition of those squares. Excellent. Okay, so that equation there looks mighty familiar. We've been through this a million times in class, but that is the adjacent squared plus the opposite squared, and then we're taking the square root there. Okay, so we're finding the hypotenuse. So the total is always the hypotenuse, and the adjacent is the resistive value, and in this case, the opposite is the inductive value. Okay, so if you're messed and you can't remember what the equation is, then you need to draw a right angle triangle. To determine whether the right angle triangle is pointing up or pointing down, we need to look at this. So we've got an Eli circuit here. So this is an Eli circuit. If you haven't heard Eli the Iceman, the Eli corresponds to the coil, the ice corresponds to a capacitor. So in this case, whatever is on the left-hand side is going to lead. So the voltage leads in this circuit, and the current lags behind. Okay, so in this case, we have the voltage being the constant. So we're going to do our triangle in this term and the fact that it's lagging behind. So if I do my x and y axes there, then I've got to draw a triangle like this. And again, if this messes you up, then don't worry about it. But the angle is right there, because the convention is that vectors are going counterclockwise. So if this is lagging behind, then it's pointing down. And we've got our resistive current here, our inductive current here, and our total current here. So the resistive current is the adjacent, the inductive current is the opposite, and the total current is going to be the hypotenuse. Okay, so we'll just be basically using that equation all the way through, Pythagorean's theorem. So we've got voltage, current, and now we've got impedance. So impedance is the combination of the resistance and the inductive reactance in the circuit. So again, this guy has physical resistance. This guy has XL, which is inductive reactance. So as you put current through a coil, it creates a magnetic field. That magnetic field cuts across the adjacent conductors, induces a voltage. So Faraday says it induces a voltage, but Lenz says, yeah, it induces a voltage, but it's opposite of the source. So it creates a counter voltage in the circuit. So the equation for this guy is a little bit dirty. So we're going to call this guy dirty Z. So anytime that you're dealing with impedance in a parallel circuit, then remember that total resistance always makes use of the reciprocal equation. So we have to make use of the reciprocal equation. So let's throw that guy in here. Okay, so that would be 1 over R plus 1 over XL. So these terms here are impedance for the Z, resistance for the R, and inductive reactance for the XL. So that's our reciprocal equation. But the other thing that happens is that those values don't come in at the same time. So we have to use Pythagorean's theorem because they're 90 degrees out of phase. So in addition to that, we're going to throw in Pythagoras here, double brackets, and then we'll take the square root of everything on the bottom here. Excellent. Okay, so that's 1 over all those guys. So putting that into the calculator, once you've done it a couple times, it gets a little bit easier, but initially it's pretty hard to get your head around trying to get that into the calculator. So we're going to try everything in our power to stay away from dirty Z. So if we need to do a right angle triangle to organize our thoughts here, then this is 1 over R. Remember, everything's reciprocals for this guy. 1 over XL and 1 over Z. The angle between those guys is right there. And then the resistance and the inductive reactance come in 90 degrees out of phase. So that's why we have this 90 degrees here. Beauty. These guys may not be drawn exactly the same, but they should be because they are the same ratio. This ratio to this, so IR over IT, is the same as 1 over R over 1 over Z. And we'll see that in the power factor in a couple seconds. Okay, the VA equation for this guy, there is no difference in the power equation for series and parallel circuits, so it's the exact same as the previous circuit. And if you haven't watched that video yet, then we have a number of different terms here as well. So VA is your volt amps, watts is your wattage or your true power, and then VARs is your volt amps reactive. So that's potential energy that's held in the magnetic field. Again, it's adjacent squared plus opposite squared. We take the square root and we find the total for the circuit. So the VA is a combination of the wattage and heat and light, and the VARs, meaning the potential energy held in the magnetic fields. Beauty. So now we've got voltage, current, impedance, and VA. Last thing we need, well, second last thing we need is power factor. So the efficiency of the circuit. This is the exact same as the previous circuits as well. Power factor is always watts over VA. So again, if we need to do a triangle here, then we'll just throw in our wattage, our VARs with a subscript L, and our VA. Same angle, so same ratio there. So that's adjacent over hypotenuse. This one's a little bit messed up because we have a double fraction. So instead of being R over Z, it's actually Z over R. Okay, so the proof for that is that if you have 1 over R, and that's over 1 over Z, well then you just take this guy and bring it up, and that is the same as Z over R. Okay, so we've got watts over VA, impedance over resistance, and we've got resistive current over total current. So those are the three ratios that we can look at for the power factor or for the efficiency of the circuit. Those guys are all the adjacent over the hypotenuse. So they're all equal to the cos of whatever angle that we're looking at. If we want to find the angle, then we're going to take the inverse cos of the power factor. Excellent. Okay, still enough equations there to make you throw up in your mouth, but you'll find that once we get to the chart, it'll be a lot easier. There is one more final equation that we have to look at, and that is this guy. We did that Ohm's law chart here on the previous examples. XL is equal to 2 times pi times frequency times L. So from that, we can get two equations. Our XL, or inductive reactance, is 2 times pi times the frequency times L. And L is going to be equal to XL divided by 2 times pi times frequency. Excellent. Okay, so if you need to, then stop the video here, take out a blank sheet of paper, and write down all these equations. It's best to keep writing them down over and over so you laser etch them into your minds, because you're going to have to know all the equations for all the different types of circuits. Okay, so stop her here and copy this down. And then what I'm going to do is I'm going to flip over to the example. So I'll put a link there for the PDF for this. But if you don't have the PDF, then just quickly jot down this example on your sheet of paper. So you have a parallel RL circuit. You have all of your total values here in this column, all of your resistive values in this column, and all of your inductive values over here. We don't have a capacitor in there, so we can scratch that portion of the chart out. So this is awesome. I didn't come up with this chart. Ted Lewis came up with this. He's my guru, my mentor, and he has an amazing way of organizing these RLC circuits. This is awesome in that we're going to find that these three right here are going to be Ohm's law. This guy right here, anything in this row right here is going to be power is equal to voltage times current. So over here for the Ohm's law, we have voltage, current, and some form of resistance, right? But that resistance could be the XL or it could be the impedance. Ohm's law works all the way through. This one here is just voltage times current, voltage times current, voltage times current for each of the different values all the way through. So you can see that 90% of the chart can be done with Ohm's law and Watt's law. Maybe one Pythagoras there. Then we're going to have to make use of the L equation and then the power factor there. Again, there are a whole whack of different ways to take on this example. But I have my answers here, which correspond to these steps right here. So in the PDF, you'll find the examples and the answers there. So I'm going to keep with these same steps. But again, you may have different steps than what I'm doing right here. Okay, so let me switch to a different pen here. Again, you can pause the video here, jot down this circuit, write down the chart, and then see if you can stay ahead of us. So you may want to pause it here, take on this example, and then follow through with the rest of the video to see if you've gotten the same values. What I'm going to do is I'm going to make use of 3 decimal places. So that way, hopefully we'll be closer. If I use 2, then we may be a little bit off. But again, you're going to be off in that the way that you tackle this one, so the steps that you take on, the different calculators will give you different answers as well. So it'll be close, but it won't be bang on from what you see on the screen here. Okay, let's try this one. Now we have a parallel circuit. This guy has 208 volts at 60 hertz for the source voltage. And we can see that that voltage goes right across to the resistor and to the coil. So first step is that we can bring that voltage right across. And remember that nothing changes with frequency there. So they're all at 60 hertz. Sweet. So now we have our voltage. Now, if I haven't mentioned it before, this is just a giant game of Sudoku in that you have 2 values now and you can find the rest of the values here. You have 2 values here, you can find all these guys. You have 2 values here, so you can come across and find your impedance. And then once we have 2 values in this column, then we'll be able to find all the remaining values. So, but I want to stay away from dirty Z. Remember, this one's dirty. That's an awful equation. So let's start off by doing our individual currents here for the resistor and for the coil. Then we'll use Pythagoras to find our total current. Okay, so let's see. We have 2.8, and we're going to divide by 50 ohms. So how did I get that? Well, that's just straight Ohm's law, right? I have the voltage, I have the, in that case, the resistance, and I'm trying to find the current there. So I've got my calculator here, which I'll bring up. So let's clear this bad boy up. What do we got? 2.8 divided by 50. It gives us 4.16 amps. Okay, so right here we have 4.16 amps. Okay, next one is 2.8 divided by 120 ohms. And let's see what that gives us. Uh, 1.733. And I just said that I was going to use 3 decimal places, and then I didn't listen to myself. Let me just go back and do that 2.8 divided by 50. Oh, okay, that was 4.16. Okay, excellent. Okay, just making sure, because if we keep 3 decimal places, then it will be closer all the way through. And I'll put a link for this guy. it's just an emulator for the Texas Instrument TI-83 Plus. So if you're doing this on your laptop or something, then you can just bring this up and use it. Or you can use your phone. All right, guys, so what do we got? We have our individual currents there, 4.16 amps and 1.733 amps. And we need to find our total current right here. Now, we can't just add those values up because those values don't happen at the same time. This current and this current are 90 degrees out of phase. So in order to find our total current, we're going to have to make use of Pythagorean's theorem. So I'll do that. I got a little bit of space right here. So I got 4.16 amps. So I'm going to take my resistive current, so I got that from here, plus my inductive current, which is 1.733. I'm going to square those guys. Remember, the square is on the outside of the brackets. And I'm going to take the square root of those guys. So let's bring up our calculator. Hopefully you've got a calculator we can do this all in one shot. So I'm going to do second function, square root. I'm going to do double brackets, exactly like I have here. I'm going to do 4.16. And I'm going to put the square on the outside. Where's my square? There we go. Okay. Plus brackets 1.733. And the square is on the outside again. Okay. Can I go back? I missed a 733. Okay. And then squared. Okay. And then I've got a final bracket to close everything up. And then I'm going to heat equals 4.506. Okay, so total current here is 4.506 amps. Excellent. Okay, so again, you can't just add up the 4.16 and the 1.733. You have to use Pythagorean's theorem in order to find that value. So we found this guy with this equation right here. Nice, and now we're rocking. Now we can find our dirty Z with just Ohm's law. So this guy is 208 volts divided by 4.506 amps. And what does that give us? And you'll have to tell me whether you like seeing the calculator here. Some people don't like it because it takes a little bit too much time. I like it because it shows everybody how I'm putting everything into the calculator. Okay, so 46.16. And that's in ohms. And does that make sense? Well, this is a parallel circuit, and 99% of the time, if you have a parallel circuit, then the total resistance is less than the smallest value. So I think we're all right. Here, the hypotenuse is larger than any other value, so the current, the hypotenuse is largest. But on this one, we made use of the reciprocal equation, so it should be smaller than the smallest value, which it is. Excellent. Okay, the rest of them, we're going to just do voltage times current there. So I'm not going to write that guy down because I don't think I'm going to have enough room to throw everything in. So I'm just going to do that calculation over here. I'm going to do 28 volts times 4.506. And that gives us 937.248. Okay. That is in volt amps. That's called your apparent power. That's the total power for the circuit. Okay, then our wattage, the heat and light that comes off the resistor, is going to be 2.8. So same voltage times what, 4.16? So I'm getting those values from here, and that's going to give me 865.28. Okay, and the units for that is watts. Okay, then we've got to do our VARs there. So again, we have 208 volts across the coil. The current through the coil is 1.733. And that gives me 360.464. And the units for that are VARs with a little subscript L. Nice, so now we found all of our power values. You can double check this by doing 865.28 squared plus 360.464 squared. When you square root, you'll get a value that's very close to 937 VA. Okay, so hopefully everything's making sense. We found our voltage, current, impedance, our VA now. Now we just have to do our power factor and our L value. So power factor is going to be watts over VA. So we've got 865.28 watts divided by 937.248 VA. Now I just used my watts and my VA. I could have also used 46 divided by 50. I could have also used 4.16 divided by 4.506. All of those guys are going to give me the same ratio all the way through. So what do we got? 865.28 divided by 937.248. And that gives us 92.3. So that on the calculator we had 0.923, right? Which is 92.3% efficient. And then if we do the inverse cos of that, let's see if can I do, so second function cos, and then I'm going to do 0.923. So you may on your calculator just to be able to do the inverse cos of the answer. And so if that's really efficient, then we should see a small angle difference between total voltage and total current. It gives me 22.63 degrees. Excellent. If you're not getting that value, then check your mode on the calculator. I'm in degrees right now. If you're in radians, then you're not going to get the appropriate answer there. It's going to give you a messed up value. Okay, so we got 22.63 degrees. That's the difference between total voltage and total current for the entire circuit. And then last step, step 11 right here, we said that L is equal to XL divided by 2 times pi times frequency. So what I'm going to do is I'm going to do the 120 ohms. I'm going to divide it by 377. So why am I dividing by 377? Well, if we take our calculator and we go 2 times pi, where's my pi? There it is there. Second function pi times 60. That's going to give me a value that's basically 377, right? 376.99. So anytime that we're using 60 hertz, you can just divide your XL by 377. So I'm going to do 120, which was my inductive reactance value, divided by 377. And that gives me a 0.318. So my answer here for the inductance is 0.318, and the units for that is in henries. Sweet. All right, so hopefully everything made sense there, guys. We found the voltage across, then we found individual currents here. Then we used Pythagoras to find our total current. We used that to find our impedance. Then we went voltage times current to find our VA, wattage, and VARs. We then took the ratio of watts to VA to find our power factor. That gave us our phase angle between total voltage and total current. And then we went back and just found the physical properties of the coil that created that XL value of 120 ohms. Right on. Okay, so hopefully everything made sense. If you like this video, then give me a like. Subscribe for more videos. So we're gonna build on this this playlist here. And if you have some positive comments, leave them below. If you got some constructive criticism, leave them below as well. And we'll see you on the next video. The next video, we'll see how I set up the playlist. I may do like all the RL circuits together and all the RC circuits together, or I may do individual circuits all the way through and then start from the beginning again. So we'll see how it goes. But in the comment section, there's a playlist that you can now follow through with a whole whack of different circuits that we can work on. All right, guys, thanks very much for your patience. We'll see you on the next video.